So no conversation about solutions would be complete without talking about the equilibria that gets established when you make a solution. So this is going to be a lesson on what we call solubility equilibria and factors that affect the solubility of substances when you dissolve them in a solute. So this process of making a solution is what we call a dynamic equilibrium, meaning things are still happening in the solution even if it looks like it is at stasis, it has stopped doing anything. So the dynamic equilibrium occurs when you add your solute to your solvent and it starts dissolving. So we have a picture on the screen of potassium chloride dissolving in water. When potassium chloride dissolves, okay, it's going to go in the direction of dissolving, but there's going to become a point where every time one more ionic coupling of potassium and chloride goes into solution, one of those potassium chlorides that are in solution will come together and form the solute out of solution, okay, precipitated out. So there's this point, it's called a dynamic equilibrium, when the rate of dissolution means dissolving, the rate of that dissolving process is equaling to the rate of the recrystallization process. So if you were to look at that beaker that had a bunch of potassium chloride sitting in the bottom and you've stirred it up and you can't get any more to dissolve, it looks like it's done. But that process is occurring back and forth and back and forth. If that beaker were to sit covered for years in a stockroom somewhere and you came back to it later, the crystals would look different because they have reformed and many times they will actually grow and look like bigger crystals. Okay? So when you've reached this point, you have got what we call a saturated solution. Okay? No additional amount of potassium chloride can dissolve, and that's when you will have achieved this dynamic equilibrium. So a saturated solution is when you have got the maximum amount of solute dissolved in that solvent at that temperature. So you add it and you know you've got a saturated solution because you added it and you stirred, you added it and stirred, and you're not seeing any more evidence of that solution, that solvent dissolving in solution. Easy to make a saturated solution with your iced tea. You put some sugar in, you stir it up, you taste it, it's not sweet enough, so you add some more and you stir it up. But eventually it doesn't get any sweeter because the sugar just sits down there at the bottom of your iced tea and you have reached that saturated point. Now, an unsaturated solution, it would be anything less than that. So if you've added just a little bit of sugar and you stirred it up and you're quite certain you could have added more, but you just like it a little sweet, you have an unsaturated sucrose solution. So it's simply added, you just add a small amount and you know most likely if it's something that dissolves at a greater amount, you're at an unsaturated point. Well, it seems intuitive that those are your only two choices. Either you've got the maximum amount you can dissolve or you're somewhere less than that. But there is a solution that is called a supersaturated solution. And what a supersaturated solution is it contains more solute in that solvent, in the solution, is more dissolved than should be at that equilibrium process. Now, there's a couple ways you can make a supersaturated solution. One way is, I had a friend and I was shocked by this. She really liked her tea sweet. So she would make her tea on the stove when it was hot and get a lot of sugar in there, and she called this tea syrup, which it is. It is more sugar and she cooled it down and all that extra sugar stayed dissolved in her tea. So that would be a supersaturated solution. So that's one way to form it. You form it by heating it up where you can get more to dissolve and slowly cooling it down, and those crystals haven't figured out, hey, we need to come out of solution and precipitate out and get back to that equilibrium and that saturated state. That's not the only way you can form this. You can form a syrup by evaporating off the solvent. This is what honeybees do. They bring in the nectar, they put it into their beehive, and they fan it, and they're evaporating off extra solvent, the extra water, and that will make it a thick honey, okay? It's super saturated, and if you've ever placed a honey bear on the shelf and come back a couple months later saying, I'd like to have some honey on my biscuit, and you pull it out, and it's all crystallized. What's happened there is it lost that supersaturated state and it came out of solution, and it looks like it's a big clump of sugar. You can redissolve it by warming it up. Okay, so solids, when you dissolve them in water, have an effect of solubility by temperature, okay? Now, this is a most statement, not an all statement. Most solids, and we're talking about solids, when you dissolve them into a liquid, are more soluble as you warm them up, okay? So like the sugar I talked about, take that table sugar and you can get more dissolved into hot tea than you can into iced tea because temperature plays that role. But that is not true across the board. And we look at this graph, and I'll move over to the screen here. We've got several substances showing an increase as the temperature goes up. But we see one example right here, and they've only presented one on here, where the temperature goes down, it gets more soluble. So that is the case where we can say most, but we need to remember that it's not all. Now, how are we going to know which ones are going to be more soluble and which one are going to be less soluble as the temperature goes up? Well, it must be determined experimentally. There is no other way. So you need to be able to read this graph and work problems from this graph. And so let's kind of look at it here briefly. This is telling you at different temperatures, okay, so we've got the temperature increasing, the solubility of that, and it's going to record it on this graph in grams of solute for every 100 grams of water. So we could pick something like the table sugar we were talking about and see how if we warmed our tea up to 60 degrees Celsius, okay, we could, if we read over here, that is about what, 285 maybe, 285, maybe 290. It's hard to read without little lines over here. I can get that many grams of the table sugar to dissolve in merely 100 grams of water. So you have almost 3 times more sugar that will dissolve in the water if you're at 60 degrees. And then if you were to let that cool down to room temperature, which is around 25, you would have a supersaturated solution. So let's work a problem here. I'll point out some things on this screen first, and then we'll go to the light board and work it. We're going to use this graph to determine if you had a 50-gram solution which had 15 grams of sodium chloride in it. We want to know whether it is saturated, unsaturated, or supersaturated at 30 degrees. So we are going to go to 30 degrees, which is right here. And we're going to find the sodium chloride line, where here's the sodium chloride, and we're going to read it to here and come over. Well, if this is 20, then this is about 40, and it looks like we can get about maybe 35 grams of the sodium chloride to dissolve at 30 degrees Celsius. All right, so this number is 50 grams of solution, and this is 15 grams of sodium chloride. If you just looked at 15 grams, you might say, oh, well, definitely that's unsaturated because this is 35. But it's a completely different comparison. Let's see if I can get back to there. Okay, it's a completely different comparison. So let's move to the light board, and let's talk about the comparison that we're seeing here. We've got ourselves 15 grams of sodium chloride in 50 grams of solution. First thing we need to note is this word right here. If we read the left-hand side of the graph, it's about water. It's not about grams of solution, it's about grams of water. Well, if I had 50 grams of solution and 15 grams of it was sodium chloride, how much water would I have? Well, what would you have to do? You simply need to subtract the two. So 50 minus 15 gives me 35 grams of water. So we've got a ratio of 15 grams of sodium chloride in 35 grams of water. Well, the table is in 100 grams of water, so I can set up a proportion here and say, well, how many grams of sodium chloride would that be equivalent to if I had 100 grams of water? So I can solve for X. I have 15 grams of sodium chloride times 100 grams of water divided by 35 grams of water, okay? And that is going to give me a value of 43 grams of sodium chloride. So 43 grams of sodium chloride would dissolve, or is dissolved, in 100 grams of and at least that is the equivalent statement. This is what we really have: 15 grams of sodium chloride and 35 grams of water. An equivalent comparison would be 43 grams in 100 grams of water. Now, if we look back at our table, we saw that a saturated solution would be 35 grams of sodium chloride in every 100 grams of water. So this is more. So we have ourselves a supersaturated solution. Supersaturated, okay? It's not a stable system, and the extra sodium chloride would precipitate out. There's too much dissolved in there. And you could have as an extra question is, well, how much of that 15 grams is going to precipitate out to give me a solution that's equivalent to that? We won't work that kind of problem, but that would be a good exercise to work through. So solids typically are more soluble as the temperature goes up. That is not always the case. You should be able to read a graph like this and make judgments as to whether a solution is unsaturated, saturated, or supersaturated. Now, what about if it's a gas dissolved in water? If it's a gas dissolved in water, the solution, we can make an always statement. And let's see if we can tag onto something to where we can remember this always statement. Now, the graph is showing us the relationship, but let's think about this. And you may or may not have done this, okay? If you were to open side by side two 2-liter bottles of Coke, so you've got a warm one and a cold one, and you open them and you listen for the sound. The question I have for you is, which one will make more noise? Now, you may not have ever done this, but the warm one will shh a lot louder than a cold one that's coming straight out of the refrigerator. So the warm one makes more noise. The question is, well, why would that be? Why would it be louder? Well, it has everything to do with the solubility. When it's warm, the carbon dioxide is less soluble in the water. The Coke contents is mostly water. Will be when it's cold, more soluble. When it's warm, it's less soluble. So you've got that head space at the top of the Coke bottle, and less of it's dissolved, so a whole lot more pressure has built up at the very top of that Coke when it's warm. And when you open it, it's escaping very rapidly. When it's cold, more of it's dissolved down into the Coke, okay? And so when you open it, there's not as much buildup of pressure and you don't hear it as loudly. Now, I like my soft drinks really very carbonated, so I like getting them really cold before I open up a can. I have been known to put them in the freezer, so it's just barely almost to freezing, but not freezing. Although I've gone too far with that. I know how to time it and be able to pull it out so that I can get the maximum amount of that carbon dioxide dissolved in there. So this is a always statement. This is not a sometimes statement. When you dissolve a gas into a liquid, it is always more soluble as the temperature drops. You can get more to dissolve in there at the lower temperature. So if you look at the graph there, all of them are sloping down, aren't they? They're all going as the temperature goes up, they're all getting less soluble. So on the side with the low temperature, it's more soluble. On the side with the high temperature, it is less soluble. Let's look at the oxygen line here, the purple line. Okay? Fish need oxygen to breathe. Oh, that's not the, sorry. Let's look at the red line. That's the oxygen, right? Fish need oxygen to breathe. They need it just like we do, and it has to be dissolved in the water. They will come up to the surface and swim around at high temperatures. When the temperature is low, they'll get plenty at the surface. On a warm day, they really have to go deep underwater, and they will dive deep down where the water is cooler, and when the water is cooler, there's going to be more dissolved oxygen in there. There have been like plants that have a stream of water near the plant, and they pull water out to run through the plant and dump it back out for a cooling system for whatever their process is. And there have been times where there have been fish kills on a river or stream while a bunch of fish die, not because they dumped poisonous water back out in that stream, but simply because they pumped such warm water back out in that stream that there wasn't enough dissolved oxygen for those fish, and they suffocated for lack of oxygen. So they have to be regulated kind of closely there to make sure that they don't dump too much warm water into the stream as they go. So that's an always statement. Solubility of gases in liquids will always decrease with increasing temperature. All right, let's look at the next one. The next one is the effect of pressure. Effect of pressure on dissolving, and we would only worry about dissolving a gas in this situation. If you're dissolving a solid, pressure is not going to affect it. But there is, when you go and let's go back to our soft drinks, and you open that soft drink, they've poured it in a beaker. I guess this is a chemistry experiment here. So they've poured it in a beaker. We know that as soon as you open it, it starts bubbling. Why is it bubbling? Well, all of that dissolved carbon dioxide was bottled in there under high pressure. The top of that Coke bottle has a high pressure CO2, which keeps a lot of it dissolved. As soon as you open it, the pressure drops. As soon as the pressure drops, those molecules are going to come and try to escape out of the solution. They start bubbling out, and it goes flat fairly quickly. Okay, so once you open it, the pressure of the CO2 is dropping and the solubility is going to decrease. So this is another always statement. The solubility of gases increases with increased pressure of the gas above the liquid. Not the pressure of all gases, total pressure above it. That won't matter. So if you took an open bottle, there used to be when I was a kid a commercial for this device that you could hook up to the top of your Coke, and you could pump it up, okay, and you're pumping it up with air, and it was supposed to keep it from going flat. Well, that doesn't work because you're pumping it up with just air, and there's a very, very little amount of carbon dioxide in air, and so you're not getting it to have more solubility of CO2, getting more other things, but that is not what gives us our the flavor that we're used to for a soft drink. Now, there is a nice mathematical relationship that helps drive this solubility relationship, and this is Henry's law. Henry's law is stated there that the concentration of your gas, now that concentration is usually reported in molarity, though it doesn't have to be. We will see other concentration units out there, but very often it is reported in molarity, and it is directly proportional to the pressure of the gas above the liquid. And if it's a direct proportionality, we can make them equal with this constant, and that's the Henry's law constant. And so Henry's law constant is going to be different depending upon the temperature of the gas, because we know solubility changes with temperature, and we have a table here of several different gases and how it's affected the solubility. Now over here I'm going to kind of draw a little graph of what we're seeing there. If this along this axis is the pressure of the gas and this is the concentration of the gas in solution, it's a straight line. It's a linear relationship between the two, and depending upon this constant, depending on which gas, some are really not as affected as much by pressure and some are highly affected by pressure. So the constant is basically telling you the slope of this line. Now, what will you be required to do with this? You won't have to memorize those constants, most certainly, but you might be given the constants and asked to make comparisons between concentration and pressure. I did not mention yet that the pressure, it is just the pressure of the gas. It's usually reported in atmospheres, but this linear relationship is going to be true whether this is in atmospheres or it's in torr. This is going to be true whether this is in molarity or some other concentration unit. So it doesn't have to be. It's going to be a linear relationship, but the constants that we're seeing here are being reported in molarity and atmospheres. So we see molarity over atmospheres as the unit. And I think if it's molarity over atmospheres, that this technically needs to be plotted with the different axes, but don't worry about it. It's still linear regardless. Okay, so let us work a simple problem here. How would we work this? In this case, we were given Henry's law constant, and we want to know the molar solubility of ammonia at a pressure of 0.1 atmospheres. Well, if this is the C is equal to K times P, and this is Henry's law constant, then we can simply use these numbers to come up with a concentration. We have the value of K sub H as 5.8 times 10 to the 1 molarity per atmosphere. I guess I need some more room here, don't I? Let's move that over. And then I would multiply by the pressure that we see of 0.10 atmospheres, and that is going to give me 5.8, the atmospheres are canceling, molar. So this is how many moles per liter I can get to dissolve in solution of ammonia in the gas. Okay, so that is one way to use this Henry's law. Henry's law is concentration versus the pressure of the gas. Let's look at another problem. This takes us back to the carbon dioxide. Carbon dioxide and Coke, okay, kind of idea. CO2 in water, it's not very highly concentrated. I mean, it doesn't give you a whole lot to dissolve in there, does it? 3.2 times 10 to the minus 2 molar, 25 degrees Celsius in 1 atmosphere. So if we had a 1 atmosphere, it bottled in 1 atmosphere, we could get 3.2 times 10 to the minus 2 moles to dissolve in 1 liter, right? And it wants to know what would be the partial pressure of CO2 in air. If you open it up, okay, carbon dioxide in the air is only 4 times 10 to the minus 4 atmospheres. Very, very low partial pressure of carbon dioxide in air. And so once you open it, the question is, what's going to be the concentration of CO2 in there? Well, I want you to start by asking yourself this. Would it be greater than 3.2 times 10 to the minus 10? Would it be somewhat close to that? Or would it be less than 3.2 times 10 to the minus 10? Well, hopefully you have an understanding of this equation. If this is dropping, this has got to be dropping. That's what this equation is saying. And it's going from 1 atmosphere down to 4 times 10 to the minus 4. It's dropping. It's dropping a lot. So now we're going to go ahead and calculate it and see what it is. So I want to show you a little trick here that you can do in this kind of situation, because they did not give me Henry's law constant. I could take the data and solve for Henry's law constant, but I can also do this. If the concentration is equal to a constant times the pressure, if I get the pressure over here, I know the concentration over pressure is a constant. And if it's a constant, that means that under each set of conditions, it's always the same value. So I can use that sort of relationship, which we kind of saw when we were doing gas laws, you know, where we came up with these change of conditions equations. So this is a similar kind of deal. We have the concentration and a pressure that we know. We know we have a concentration of 3.2 times 10 to the minus 10, and that is in units of molarity, if the pressure of the gas, of carbon dioxide gas in this example, is 1 atmosphere. What we want to know, sorry, I don't want to times, what we want to know is what would be the concentration if the pressure were 4.0 times 10 to the minus 4 atmospheres. Since this is much lower, this will be much lower in order to give that value. So when we solve for x, we will know how much will dissolve at normal atmospheric conditions of carbon dioxide. And I've got a value for that somewhere here. It is 1.3 times 10 to the minus 13 molar. So this is what the concentration drops down to when you open up a Coke and let it sit in the atmosphere. It drops the concentration of carbon dioxide way down. And that's why it's busy bubbling away in your glass as that concentration is driven out of there. Okay, so we have, let's see if there's anything else. No. What we have here in this lesson, we saw how concentration is affected by temperature, and that's whether it's a solid or a gas, and we saw how the concentration was affected by pressure and worked some numbers with that.